for silicon. So let us see for silicon case. Okay, if we go for silicon, EK space diagram for silicon, the here if we see the minimum conduction band energy and maximum valence band energy do not occur for the same value of K. Do not occur for the same value of K. If we draw here this EK space diagram, so this is our EK space diagram. Let us see. This is zero. This is my momentum. This is my energy. And okay, so here somewhere it will start here, and this is so this is my minimum here, minimum, and here this is maximum in case of valence band. Okay, so now see minimum. This is what minimum of the conduction band energy we see, and this is what EV, maximum of the conduction band energy that occur for K equal to zero value, but here minimum conduction band energy that does not occur at K equal to zero. Okay, so there is a difference, but it occur in what, in which direction? In 100 direction. 100 direction is nothing but it is a face centered cubic structure. Face centered cubic structure in 100 direction. This is nothing but 100 direction is nothing but face centered cubic structure, means this is like this. These are my face centered cubic structure. Okay, so 100. This is like a B. Okay, K space direction, in K space direction. So this is direction. This is what 100 direction. Okay, so it does not occur at K equal to 0. So therefore there is a difference. Means here momentum is not conserved. Okay, momentum is not conserved because if you want to adjust, if you want to make it direct nature, then we have to move this to this side, means it should move like first this. There is no momentum, there is no conservation in momentum. Okay, it should first K is not equal to 0, in the sense K is not equal to 0. For that it should move somewhat distant, okay, from here to here. Okay, then after that it will come in it will come in the direct contact, and after that there is what, there is a transition of electron from conduction band to valence band. Okay, conduction band to valence band. If we see for this here in simplest form, here this is conduction band, valence band. Okay, so this is not here direct, so it is somewhere here. Okay, so now see here. First this has to come here, then after that there is a direct contact. So this is my K and this is my energy in electron volt. Remember, this K is not directly what momentum. This is actually a K space. This K is nothing but wave propagation vector. What? Wave propagation. Wave propagation. It is actually a wave propagation vector. Okay, so it is actually a wave propagation vector. Okay, so and this K is related to what? P by H cut. P by H cut. So P is what? Momentum of free electron. Okay, momentum of free electron. So therefore this K for free electron is what? Momentum. Okay, so now see here, we are here. Okay, so this momentum here is not conserved. Momentum is not conserved. Energy is also not conserved. Means here the energy that will come out during what? That will come out during the recombinations of electrons and hole pair. During the recombination of electron hole pair, the energy that will come out is not radiative. It is non-radiative. Means energy is consumed. Energy is consumed and it is dissipated in the form of heat. In the form of heat. Okay. If you see when we will adjust this to here, then it should move. Here K is not equal to 0. Means this momentum is not conserved. If momentum is not conserved, then energy is also not conserved. Energy is not conserved in the sense that during the recombination of recombination of electron hole pair, okay, during the recombination of electron hole pair, whatever the energy that will come out, okay, that will come out, it is a type of non-radiative in the sense that not conserved energy is not conserved means here energy is consumed means energy consumed means it will dissipate in the form of heat, okay. Okay, so remember here in case of gallium arsenide, in case of what gallium arsenide, see difference. This is what my in case of gallium arsenide. What gallium arsenide? This is my in case of gallium arsenide, and this is my in case of silicon. What in case of silicon? So this is my in case of silicon. This is my in case of gallium arsenide. Okay. So this is my K. This is my K, and this is my energy. Okay. Energy in electron volt. Energy in electron volt. Okay. Energy in electron volt. See the difference properly. What is the difference? This is for gallium arsenide, and this is for. I think it is not visible here. So just what I should do. First understand this, then after that we will come to conclusion. Okay, so we will come to conclusion. First we will complete this. Now see here what happened. This electron has to move here. Okay, to make this in direct contact. So therefore when it will come here, when it will come here, see here, when it will come here in direct contact, but there, this is my K and this is my E. Okay, so now see here, momentum is not conserved, means K is not equal to 0. So this means the energy is also not, what energy is also not conserved. Energy is also means it has to move some distance. It has to move some distance. For that it should consume some energy. It should consume some energy during this transition of electron. So during this transition of electron from conduction band to valence band, okay, from conduction band to valence band. So let us say this is my conduction band, this is my valence band. Okay. So during the transition of electron from conduction band to valence band. So there is what now the energy that will come out. The energy that will come out during the recombination of electron hole pair. During the recombination of hole pair is a type of non-radiative nature. Means here energy is what consumed. Energy is consumed means energy is what dissipated. Energy is dissipated in the form of heat. Okay, so h nu is equal to h nu. It is a energy in the form of heat. Okay, so it is a energy in the form of what? Heat. It will get dissipated. Energy will get dissipated here. Okay, so it is in the form of heat. But in case of direct band gap, this energy is in the form of photon. Their energy has consumed. Here energy is not consumed. Okay, energy not consumed in the sense that energy is a non-radiative type of energy. Means here energy will get dissipated. Dissipated why? Because here the electron has to move some distance. Means it has to move some distance. Means k, no, k value is not equal to 0. If it has moved to some distance, means it has consumed some energy. It has consumed some energy. That energy will consume during the recombinations of electron hole pair. Electron hole pair. Okay. So where the electron will get transient. Electron will get transient from transition. Electron will get transition from conduction band to valence band. Okay. So now here again, what we will see here in this case, the electron that make the transition. So therefore, the electron that make the transition between the conduction band and valence band, and it is what? It is an indirect band gap semiconductor. Yes, indirect band gap, indirect band gap semiconductor. Okay, so indirect band gap semiconductor. Now, what the thing is that during the transition of electron, during the transition of electron from conduction band to valence band, conduction band to valence band. Then in that case, we should invoke law of conservation of momentum. We should invoke the law of conservation of momentum, because here the momentum is not conserved. Yes, not conserved. Why? Because the electron has to move some distance in such a way that we can make it direct in nature. Okay, we can make it direct in nature. So during that, for that we must invoke, or we must use the law of conservation of momentum. Okay, law of conservation of momentum must be invoked. So here we must invoke law of what? Law of conservation. Law of conservation. Law of conservation of momentum. What? momentum, momentum. Yes. So that is what during during the transition, during the transition of what? During the transition of electron between conduction band and valence band. Okay, so that is what when transition occur for the electron between the conduction band and valence band. That time we must invoke the law of conservation of what energy, law of conservation of energy. Okay, so now next is what? Next is that next is that in this indirect band gap, material. Okay, so this in this indirect indirect band gap, in this indirect band gap material. Okay, so in this indirect band gap material, the transition transition between conduction band and valence band, transition between conduction band and valence band must what? Must include what? Must include interaction, must include the interaction with what? Interaction with crystal. In what instruction? That is interaction with crystal. Okay, with crystal. So that crystal momentum, so that crystal, so that momentum, crystal momentum is conserved, is conserved. Okay, so that is what for indirect. In this indirect band gap material, the transition between conduction band and valence band, that must include what? Interaction with crystal, so that crystal momentum is conserved. Okay, so these are the some factors that we have to keep in mind. Okay, while discussing the EK space diagram for silicon. Okay, so this is what about EK space diagram for silicon and gallium arsenide. If we see some conclusion, okay, summary about this, both gallium arsenide and silicon. Both gallium arsenide and silicon. Let us see here. So this is for what? This is my EK space diagram. This is my EK space diagram. Let us say here this. Okay. So this is for my what? For gallium arsenide. Gallium arsenide. Yes, what? EK space diagram. EK space diagram. So now if you see here, there is a what? Direct nature. Okay. So let us say this boundary is what? Pi by a, and this is minus pi by a, this is plus pi by a. Okay, because we have to limit ourselves within one period. This is about one period. Whatever information we will get under one period about electrical property, optical property, for all the other period we will get same information. So therefore it is better to confine or limit ourselves within one period. Okay, one period. So therefore it is a portion of that all the largest waveform, which is periodic waveform. Okay, so this is for gallium arsenide. And similarly if you see here this band gap, this contact is not direct. Okay, so this is what EC, this is my EV, maximum valence band energy and minimum conduction band energy, both are in direct nature. Okay, both are occurring at k equal to 0. But here it is something different. Okay, so that is like this. So this is k, this is E, electron volt, this is momentum, means it is not directly momentum, it is related to momentum. It is a wave propagation vector. What? Wave propagation vector. Okay, so which is related to what? Here k is equal to p by h cut, p by h cut, p by h cut. Okay, so this is momentum, this is related to momentum. So k for free electron is related to what? Momentum. Okay, so this is for what? Silicon. This is for silicon. Here you see they are not in direct nature. So this much distance, this electron, this much distance, this electron has to move. Okay, in such a way that it will come under direct contact. So for that we can say that the momentum is not conserved. Here momentum is not conserved. Here momentum is conserved. Here energy is also not conserved. Here energy is conserved. Here both energy and momentum is conserved. But here both energy and momentum is not conserved, because how much distance this electron has to move, that much energy it must consume. That much energy it must consume, or it must what dissipate. Okay, or either it must consume or it must dissipate in the form of heat. In the form of heat means here whatever the energy, let us say this is what energy whatever during this transition. Okay, so during this transition whatever energy will come out, whatever energy will come out, that is in the form of what? Heat. That is in the form of heat. Okay, so that is in the form of heat during the transition of electron from conduction band. During the transition of electron from conduction band, this is my EC and this is my EV. Okay, so let us say this is my valence band and this is my conduction band. Okay, so whatever the energy that will come out during the transition of electron, or you can say during the recombinations of electrons and hole, the energy that will come out is a type of non-radiative in nature. That is type of non-radiative. Okay, so it is a type of non-radiative in nature. Okay, so therefore which means the energy is dissipated. Energy is dissipated, it is not consumed. Energy is not what? Energy is not conserved. Okay, it is dissipated, either it is consumed. It is dissipated in the form of heat. But here if you see here, whatever the energy that will come out, during the transition of electron from conduction band, during the transition of electron from conduction band to valence band, that energy is what? Radiative in nature. What? Radiative. That energy is, that is right here, this energy is what? Radiative. This energy is radiative in nature. Okay, so this energy is radiative in nature. Okay, so therefore here energy is conserved and momentum is also conserved, and this energy is something like photon, and energy of photon, that is equal to what? That is further equal to Eg. Okay, so this is what equal to Eg. Eg means energy band gap. How much energy band gap is there, that much energy will get radiated in the form of photon. Okay, or you can say in the form of light. Okay, so this is photon in the form of photon, or you can say it's the light in the form of light. Okay, so in the form of light. So therefore this direct band gap semiconductor material, that is useful for what? For LED, laser, okay, and other optical devices. But these, the semiconductor like elemental semiconductor like silicon and germanium, these type of semiconductor are indirect band gap semiconductor material. So they are not used to not used for LED, like LED, laser, and other optical devices. Okay, they are normally used. Okay, so they are normal semiconductor material. They are normal. Okay, so now this is what the most difference that we will get in both cases: gallium arsenide and silicon. Okay, gallium arsenide, silicon. Here the energy that will come out, that is non-radiative. Here radiative. Non-radiative means it is dissipated in the form of heat. Either it is consumed. Okay, but it is not coming in useful manner. If it is will come useful manner, means the energy is conserved. Energy is conserved. Here both energy and momentum is conserved. Here both energy and momentum is not conserved. So therefore, during the transition of electron from conduction band to valence band, here energy is radiative in nature, that is coming out during the transition of electron. Here the energy is non-radiative, that will come out during the transition of what? Electron from where? Conduction band to valence band. Okay, so this is most of the difference that we can get in both case. Okay, for gallium arsenide and silicon. Okay, so this is something, some factor that we have discussed. Okay, so now if you see here, there is a some what there is a compound semiconductor that is also indirect band gap semiconductor material. If we see for what? Gallium arsenide. Gallium arsenide is what? Gallium arsenide is what? Direct band gap semiconductor material. Direct band gap. Yes. It is direct band gap material. It is direct band gap material. If I will say gallium phosphide, it is indirect. What? Indirect. It is indirect band gap. It is indirect band gap. It is indirect band gap material. Material. So if I will say aluminum, aluminum arsenide. Aluminum arsenide, this is also compound semiconductor, but indirect. What? Indirect band gap. It is also indirect band gap material. It is also indirect band gap material. Okay, so this is something about compound semiconductor. Okay, and silicon, germanium, both are indirect. Both are indirect band gap. Both are indirect band gap material. Okay, so both are indirect band gap material. So this is what all about the EK space diagram for both gallium arsenide and silicon. Okay, compound semiconductor and elemental semiconductor. Both we have seen. Okay, so now we will go to next. That is about. Okay, so this is all about this. What the EK space diagram for gallium arsenide and silicon. Okay, so thank you very much. Okay, for supporting me and watching my lecture. Okay, I'm so glad if you are watching and supporting. Okay, so thank you very much.